So after discussing simple harmonic motion, let's now move on to the nature of waves. In this lesson, we are going to answer what is a wave and what are the different parts of a wave and also its different characteristics. We will also try to solve problems about waves and its properties. Okay, what is a wave? For example, you toss a pebble in the water, you can see that there will be a ripples. So that is actually a wave, which is caused by any disturbance on the water. And that wave travels outward in all directions. So a wave is produced by any disturbance. And also what is being transferred by a wave is energy. Do you think particles are transferred by waves? Okay, it is not the particles which are transferred, but again, it's the energy being transferred by the waves. We have two examples, or we have two types of wave. We have a longitudinal wave and a transverse wave. For the first example here, if this one vibrates at this motion, or it's a horizontal motion, we call that a longitudinal wave. But for this one, if you're going to produce a disturbance which is up and down, then you have here a transverse wave. Okay, you can see there. Looking at the longitudinal wave, we can say that the particle movement or the direction of the particle movement is parallel with the direction of the energy transport. For a transverse wave, the particle movement here is up and down, but the direction of the energy transport is, say, to the right, so they are actually perpendicular. The direction of the particle movement is perpendicular with the direction of the energy. Here are the different parts of a wave. Particularly for a transverse wave, we have here the amplitude, or the height of the wave, the crest, which is the highest point of the wave from the equilibrium position. This one is the equilibrium position. And then the trough, they are the lowest point of the wave. And then we have here a point from, let's say, trough to trough is one wavelength. And a point from crest to crest is also one wavelength. Okay, again, we define a longitudinal wave as this one. The direction of the movement of the particles is the same with the direction at which the wave moves. For a transverse wave, the direction of the movement of the particles is perpendicular with the direction at which the wave moves, or at which the energy moves. Okay, let's take a look at this one, which is a sound wave. So sound wave, do you think it's a longitudinal wave or a transverse wave? Okay, so you can see here, sound wave is a longitudinal wave. And here are the parts of the sound wave. Okay, we have here compression, wherein these are the regions of high air pressure. You can see there yung red part, that is compression, where the waves are compressed. And then the regions of low air pressure, where they are not that compressed, that is rarefaction. So again, yung may red, that is compression. And then yung mga blue lines, that space is the rarefaction. Okay, we also have another type of a wave. Before that, take note that sound wave and water waves, they are examples of mechanical waves. For mechanical waves, they need medium for you to be able to transfer energy. For example, in water, you need water particles for you to be able to transfer energy. For the sound wave, let's say you need air so that you can transfer sound, or the energy coming from the sound. Okay, for electromagnetic waves, they can be transported even though you don't have a medium. So for example, light waves. So you can propagate, or they can be propagated kahit walang air. Or you can transfer light. Okay, you can propagate the energy of light even though you are in a vacuum. And here is an electromagnetic wave. It is composed of two equivalent oscillating electric and magnetic fields. Yan. One is electric field and then the other is magnetic field. They are perpendicular from each other. And they are also perpendicular to the wave propagation or to the direction of the waves. That's why electromagnetic wave, they are known to be transverse waves. Now here is the composition of electromagnetic waves. We have the radio waves, microwave, infrared, visible waves, ultraviolet, X-ray, gamma rays. Now in waves and optics, when we reach optics, we will focus on the visible range, okay, or the visible electromagnetic waves. Okay, again, mechanical wave, they need medium or they need media to transport energy from one location to another. Okay, I'll show you a demonstration on this one. Let's see if we can play it. Okay, now let's take a look at this demonstration. So you can see here we are producing 500 hertz of sound. And then let's try to remove the air from the box. Okay, and observe what happens. Now it's trying to remove the air from the box so that it will become a vacuum. Okay, so you can see now there's no pressure, so there's no air inside the box. Can you hear any sounds? Okay, no, because sound needs medium for it to travel. Let's take a look at the different measures of a wave. We are going to define the following: frequency, amplitude, speed, period, and wavelength. Okay, when we say frequency, this is the number of vibrations per unit time. Kung ilan yung vibrations, like for example in this one, we have here crest to crest, that is one vibration, okay, one, then another crest to crest, two, okay, three, four, five. So we have five vibrations or waves passing through at that point at a particular period of time. Of course, we have to note the time. Okay? So it is also considered to be the reciprocal of period. So now let's define period. Period is the time needed to complete one vibration. This time, isang vibration lang. Ano yung time para makomplete niya yung isang vibration? So it's also a reciprocal of frequency. Okay, now let's define wavelength. The wavelength corresponds to the distance traveled by the wave is from crest to the succeeding crest or from trough to the next trough. That is the wavelength of a wave. For the amplitude, let's say we have this one. This is the equilibrium position. This is the highest point of the wave, which is the crest. Okay, the distance from this equilibrium to this point, that is the amplitude, or also known as the height of the wave. The height of the wave also tells us about the amount of energy that the wave carries. The higher the amplitude, the higher is the amount of energy it carries. The lower the amplitude, lower yung energy. Okay, now let's take a look at the wave speed. In kinematics, recall that speed tells us about how fast an object moves. It is also telling us about the distance covered per unit time. So, assuming that the wave is moving at a constant speed, the speed of the wave can be written as follows. You have here velocity. Let's say the distance it will travel is equal to one wavelength, so that is wavelength. And then the time needed for that one wavelength to pass through is equivalent to period. So this one is like distance over time, or we have here wavelength over the period. And let's also recall that period is the reciprocal of the period is equal to frequency. So we have here lambda times f, or we have the wavelength times frequency is also equal to the wave speed. Now, I want you to reflect on this one. This is also related with waves. As I have mentioned, any disturbance can actually cause waves. So same with ripple effect. It is stated as this one: offer one small act of kindness, and in the moment it is gone. But 100 ripples circle on and on and on, and 100 ripples circle on and on and on. So you never know what ripples your words or actions might make in the lives of others. That's according to Cheryl King from her book Ripples of Joy. So in your reflection part, or in the reflection part of your module, I want you to reflect on this one. What ripple effect would you like to make on others' person's lives? Okay, so okay, our first problem would be this one. When a family of 4 people with a total mass of 200 kilograms step into their 1,200 kilogram car, the car's springs compressed by 3 centimeters. What is the spring constant of the car's springs, assuming they act as a single spring? So we have an equation, F, or the restoring force, equals negative kx. But what is the force acting on the spring? We have the 200 kilograms. But we have to convert the mass into Newton, so we multiply by 9.8 meter per second squared. So that will give you a total force of, okay, the force now is equivalent to 1,916 newtons. So next is that we are going to look for K. Deriving the equation, we have K equals negative force divided by X. So we have the force of 1,916 newtons divided by, our X is 3 centimeters, but you have to convert to meter, so that will become 0.03 meter. And it's also compression, so that will be negative displacement. And then our K now, or the value for K, is equal to, so the value for K is now 65,333, or we can also express it as 6.5 times 10 to the positive 4. The unit will be newtons per meter. Okay, that is the spring constant. Now the next problem is estimate the length of the pendulum in a grandfather clock that ticks once per cycle. What would be the period of a clock with 1.0 meter long pendulum? So our formula for period equals, for a pendulum we have 2 pi, square root of length over acceleration due to gravity. Okay, for the period we have 1 second. Okay, again, that is our equation. Now let's derive an equation for the length. So let's square both sides. We have t squared equals 4 pi squared, then L over G, because we can already remove the square root. Then for L, we now have, okay, let's derive an equation for L. We have L, t squared times G, all over 4 pi squared. So the given period is only 1. Then G equals 9.8 meter per second squared, divided by 4 pi squared. Okay, our answer is 0.25 meter.
Okay, just to show you the cancellation of units, for period we have second squared, and then for acceleration due to gravity we have meter per second squared. We cancel out second squared, so our unit is in meter. Okay, the next is, what would be the period of a clock with 1.0 meter long pendulum? Originally, it was 0.25 meters. So our formula is T equals 2 pi square root of L over G. Okay, period is directly proportional to the square root of L. Since you have 2 pi and G as constant, so we can just use the length. So period being directly proportional to square root of L, let's check on the relationship of what will happen. Period is directly proportional to the square root of 4, so it will become twice the original period. Okay, looking at this, the period doubles because you have multiplied the length by 4. So as you can see, the relationship is that period is directly proportional to the square root of length. Okay, for the next item, we have an athlete paces back and forth along the field 20 times in 3 minutes. What is his frequency in hertz? Okay, let's now solve for frequency. Frequency is the number of vibrations per unit time. So that is our formula. Okay, the number of vibrations we have 20 times divided by we have 20 vibrations divided by 3 minutes. However, you have to express 3 minutes into seconds. So let's convert. 3 minutes, we have 60 seconds in 1 minute. There, that is our unit conversion, 60 seconds per 1 minute. And that is equivalent to 180 seconds. So we have frequency is 20 vibrations divided by 180 seconds. Okay, equals 0.11 hertz. Okay, next problem. A wave on the Angat Dam passes one duct every 10 seconds. What is the period of the wave? So again, period is the time needed for one complete vibration or for one cycle. Since there is only one wave passing through it every 10 seconds, so that is already our period. The period is just equal to 10 seconds. Next, a tuning fork has a frequency of 512 Hz. What is the period of this tuning fork? Okay, we have frequency given is 512 Hz. Okay, period is just equivalent to reciprocal of the frequency. So we have 1 over f and 1 over 512 Hz. Okay, our answer for period is equal to we now have 0.002 seconds. Okay, again, take note or recall, we have here 1 hertz is equivalent to 1 over second. Okay, if we have an equation 1 over 512 hertz, so that is 1 over second, and that is equivalent to the unit of seconds. Alright. Okay, next, A wave generator produces 20 pulses with a speed of 2 meters per second in 2 seconds. What is the wavelength of the wave? Okay, we have here velocity equals lambda f, or wavelength times frequency. Okay, our frequency is the number of vibrations per unit time, or the number of pulses per unit time. That is equivalent to 20 pulses per 2 seconds. So the frequency that we have is 10 hertz. Okay, let's solve for the wavelength. Okay, wavelength is equivalent to the velocity over the frequency. So we have our velocity is 2 meters per second divided by 10 hertz. Okay, cancel na natin ang seconds. So the final unit for a wavelength is meters. Okay, our lambda now is equal to 0.2 meter. Okay, next item. A water wave in Laguna Lake passes two shores which is 200 meters apart. If each shore has trough and another 19 troughs between two ports, what is the velocity of the wave when 30 waves pass one port every 25 seconds? So now, how do we solve for this one? For example, you have two shores. Then you have the trough. Okay, for example, 30 yan. We have 30 waves passing through it. I could no longer draw the 30 waves. But take note of this. Okay, take note of this one. Trough to trough is equivalent to 1 wavelength. Then crest to crest is also equivalent to 1 wavelength. Okay, in these illustrations, we have 1, 2, 3 crest. So that will be 2 wavelengths na. So in our problem, we have 1 trough per shore. Then meron pang 19 troughs between the ports. So we have total of 19, 20, 21. Yeah, 19 plus 2, we have 21 troughs. So we have to subtract 1 so that we can actually get the wavelength. Okay, so we have now, okay, 21 troughs minus 1, we only have 20 wavelengths. Just like in our example, we have 3 crests, pero dalawa lang yung wavelengths. So we have 20 cycles in this problem. Okay, again, we have from shore to another shore, we have there a distance of 200 meters. So we have to divide the 200 meters into 20 cycles so that we can get 1 wavelength. So our wavelength is equivalent to 10 meters. Okay, let's continue. We have the wavelength is 10 meters. Okay, we have the frequency is the number of vibrations per unit time. Okay, we have 30 waves passing through it every 25 seconds. So let's divide that. 30 divided by 25. We have a frequency of 1.2 hertz. Okay, next is to solve for the velocity. Okay, we now have velocity equals lambda f, or wavelength times frequency. We have 10 meters times 1.2 hertz. Okay, so that is equivalent to 12 meters per second. The next problem that we have, water drops are being dropped into a body of water at a rate of 43 drops every 60 seconds. The distance between crest and the seventh crest is 2.4 meters. Find the speed at which the waves are traveling. So now let's draw the waves. Pagpasensya nyo na yung drawing na yan. So let's have 7 crests. Okay, the distance from the first crest to the last one is equal to 2.4 meters. Okay, just like in the previous problem, kung kanina we have 21, we subtract 1, so we have 20 waves. Right now we have 7 minus 1, then we have 6. Okay, we have 6. Okay, so we now have 0.4 meters. Now let's solve for the frequency f. Okay, we have 43 drops for every 60 seconds. 43 divided by 60, our frequency now is equivalent to 0.72 hertz. The next one is that we have to solve for the velocity. Velocity equals lambda f. Okay, our lambda is 0.4 meter. And then frequency of 0.72 hertz. Okay, our answer is... we have now 0.29 meters per second. Bye everyone! Happy learning! See you in the next video!